Welcome all. So, the first example is the class of algorithms where estimating, or I will call that as implicit latent variable models. And by the way, this nomenclature is not standard, you cannot find this in any textbooks. I am just making I am just giving a name here. So, here what we have is that Px is estimated via an implicit latent variable model So, let us take a few examples on this. The first example is where I use a linear model. And I am reiterating, please note that everything that we do in a non-probabilistic ERM way also has a exact correlate in the probabilistic space, and I will keep switching between these two. So far what we saw in k-means and GMM are the probabilistic ways of looking at it. Now we will look at the ERM way of doing it. So, linear model on data. So, what do you mean by linear model on data? Let us say that X is in RD and we have the data set that contains n data points. Now, another thing to recall here is, which I had mentioned in the previous class as well, is that one other advantage of getting these representations, okay, is compression. I told you that typically the dimensionality of this latent variable z is much less than the dimensionality of the data variable. Okay. In clustering itself we saw, clustering is also a one sort of discrete representation where suppose you have thousands of dimensions of data, you compress it into a 10 dimensional space, discrete space, if you are doing a 10 way clustering. Okay. Now, why is compression important? This is again takes back to the information theoretical space, that see, we do not have an understanding on why these today's models have actually become intelligent. All we are doing is ERM, okay, on these transformer kind of models in an unsupervised way. I will show you how it is done in an unsupervised way. Now, why are they becoming intelligent is because there is compression that is happening. So, according to one theory, compression gives you intelligence. So, why is that? Because the data, I mean, if you want to compress, reduce the information and take the information from a very high dimensional space and put it into a very low dimensional space, the best way to do it is by understanding the underlying semantics. If you do not understand the underlying semantics, then you cannot compress. Let me give you an example. Let us say that I give you a picture of human faces, multiple pictures of human faces, and I will ask you to represent this using 10 numbers. Okay. How would you do this? The first thing is you will identify that all human faces have a symmetry, that there are two eyes, so there is a nose and there is a mouth and all that, okay. And perhaps you will see that you will store all this information in 4 bits, that there is symmetry, there is nose, there is eye and all that, and then maybe store coordinates of where the eye is and all that. So, now there will be loss of information, of course, because you are only given 10 dimensions, but the best way to compress is to understand what the underlying semantics is. Does it make sense? Because everything else is useless information. Right? Okay, there are so many skin pixels. Okay, what do you do with it? Fine. I mean, you can just get the skin color and then maybe paint it. So, compression means semantics. So, unless you understand the underlying semantics well, you cannot compress. Now, what is happening is, in today's AI or all these models, what is happening is, the entirety of the human knowledge that is stored in internet as text, image and all that is now being compressed into 5 billion parameters, right. If that were to happen, The only way to do that is to get the underlying semantics. Okay. That is why that's the power of unsupervised learning or learning representations, because you are compressing that way. Okay. So, now we will look at a small, I mean a very naive way to compress the data, which is a linear way of compressing data. We will assume that there exists a Z that is in k dimensional space. Typically k is much less than d. We want to compress the data. Okay. Now, we will define some V to be equal to a matrix W times X, where W is a K cross D matrix. This is a K cross D matrix, and this is a D cross 1 vector. Actually, let me just change the notation a little so that we will consistent. Yeah, Z can still be in hold on. So, Z can still be in RK. So, what we need is, we want the Z to be equal to, do not copy it yet, let me just see this notationally consistently. So, we want a linear projection space W such that when you project your data onto that space, you get a k dimensional compression. That makes sense, right. So, the goal objective here is to learn a linear projection W such that the data gets compressed from dimension D to dimensions k. Does it make sense? So, this is again learning an implicit latent variable model. In fact, this you can see this as an explicit latent variable model as well via a linear projection. You take X, project that onto some space defined by W. You all know that multiplying a vector with a matrix is equivalent to projecting it onto a space spanned by the columns of this matrix, right. So, that is why this is a linear projection that we are doing. So, the question that we are asking is, we take a data point, project it onto a space given specified by a matrix, and after projection we want the data to be compressed into a smaller space is the idea, and we use Z as our representations. Make sense, right. So, now the question is, how do we get this W? We will have to what is the best way to get W is the question. Okay. Now, question, obtain W by solving, this is not a question, how to obtain W is a question. Such that some criteria has to be optimized now, correct. Now, if we were to do this in the probabilistic space, we would say that, oh, there is a distribution on this and we would want to minimize the divergence. So, since we are operating in the non-probabilistic realm, so how do we say that? We will define a loss function, okay. So, such that a loss function is optimized. Okay. So, we can define a particular loss function, which is define the loss function as now, what can be a good loss function? There can be multiple ways to do this. One way to do it is that the variance of the projected data has to be minimized. So, I want to project in such a way that once I project, the spread of the projected data has to be as small as possible. Why is this a good objective function? Think about it, we are trying to compress the information. When we are trying to compress the information in smaller number of bits, okay, once you project the data has to have as less variance as possible in the projected space, because that will give us the maximum compression, isn't it? Spread or the variance of the projected data can be looked into as, how much, I should not be using the word divergence, and how much spread that particular data has, okay, in the projected space. Because we are seeking compression, we will have to, one good objective would be to let the algorithm decide what sort of projection would give me the least variance in the projected space. Okay. Define the loss function as that of minimizing the projected variance. Which is, so Zi is our projected data. If Zi is the data point, so we have n data points, right. So, this is the mean of all the data points. I am just writing the empirical estimate of the variance. We will have to take a square of this, right, square this and add them over all data points and divide by n. So, this is our L, loss function, and this depends on W, right, because Z depends on W. In fact, it depends on W and also, okay, what was our notation? It was L theta, is it? L of theta or L subscript theta? The parameters were we writing our parameters as subscripts or the arguments? L of theta, right. So, okay, we will write it as L of W comma x. X is data and W is your parameter. So, this is the loss function. So, what do we need? We want our W star such that this is minimized.
Aren't there no other constraints, because we can put Zi to all zeros?
We will get there. Okay. So, what does this come out to be? Let us write down this loss now as I beg your pardon, I think I made a mistake in formulating. It should be, see, mathematically it does not matter, but interpretation is what I changed, okay. It should not be minimizing the projected variance, it is minimizing the negative of the projected variance or maximizing the projected variance. I think that is where I made a mistake. Let me just rewrite it. I can write it as negative of this, but yeah. Now, we will have to change the interpretation, right. So, I think I made a mistake. Can somebody point the mistake?
Like we want to find those predictions in which the data has the maximum spread, so that like those are the most important representation.
See, okay, what did I say? What was my interpretation? I said the variance has to be minimized. It is not, you want to say something? Yeah. See, the thing is, please you should note that Z by construction we are saying that it has to have lesser dimensions as data. But the question that you should be asking is, how should I choose my projection in such a way that the directions that I choose or the projections that I choose will preserve the variance of the data to the maximum possible extent. Now, because I do not want to lose the information. See, I will tell you why I made this mistake. There is another equivalent interpretation of this, okay, which I will tell you at the end of this particular discussion. I think I just mixed up both of them, but did you get the idea? The idea is once you project onto a subspace and trying to compress it with using lesser number of dimensions, you will have to project it in such a way that the variance of the projected data is maximized, because you want to preserve whatever spread that was there in the initial data on the projected space as well, notwithstanding the fact that the dimensionality of the projected space is much less than that of data. Right. So, just hold on, we will do the math and we will see what the solution is going to be, and then I will tell you an equivalent minimization formulation of this, okay, where the interpretation sort of changes. That is where I made that mistake. Is it clear? No? What is not clear?
So, if for example, the example that you gave of faces, if I am projecting it down to, let us say, 10 numbers, and one of them is whether the face is of a female or a male. So, I can't have variance there. It should be a deterministic answer that this face is male and this face is female. So, that is equivalent to reducing the variance. But
no, not necessarily. Let's see, if you think of it from the continuous variable perspective, that is easier to interpret that way. So, let us take a continuous variable. So, let us say that you are measuring the width of the eye in the actual phase, and you have 100 pixels to do that. Now, all those 100 pixels are now compressed into, let us say, 4 numbers. Now, those 4 numbers have to be in such a way that the spread of information that was there for all the eyes in the original data set has to be preserved here. Otherwise, it will be information loss.
that statement did not make sense to me.
Why is that?
I mean, can you take a different example than width, because width also is a spread. So, are you saying
No, width is a number. I am saying, let us say that there is a scalar. Okay, the information about the width is compressed or rather embedded in 5 dimensions in the original space, let us say, or 10 dimensions in the original space, let us say. They are 10 pixels. Now, you want to compress all of that into, let us say, 2 pixels. Now, all the information that was there regarding these the width, which is the parameter that is being measured in the original data space, has to get reflected in your projected space as well. How is that possible if you do not maintain the same variance that was there in the original data space corresponding to this particular feature in the projected space as well? What happens otherwise is all the let us say that there is the variance is minimized for that particular feature, or rather you seek a particular projection such that the variance is minimized. So, what will happen is it will create a degenerative case where it will nullify different widths of all human eyes and put it into a one data point and say that there is an eye. We do not want that to happen. So, we want the measurement that we have made. See, actually here is the point. The point is whatever is redundant has to be taken off. Whatever is informative has to be maximized. That is it. Right. So, how do you quantify the informativeness is through the variance of the projected data. That is the idea. Is it okay now? Okay. So, now let us look at this. How do you solve this problem? Is this is equal to see, I keep telling this jokingly to my students always, that as engineers you solve a problem empirically first and retrofit the math. That's how most papers are written, by the way. See, when you write a paper, you first say that, oh, this is the problem that we had, and here is a theorem, here is the lemma, this is what we solved, and then we talk of experiments. But research happens exactly the opposite way. So, you try 10 different things, something works. So, you get an empirical result. Okay. My kind of one of my favorite statements that I keep telling my students is that if there is something that is working empirically, then there should always be a math that explains it. Right. So, that is how it is. Right. So, sometimes what happens is you start by hypothesizing something and write an equation and then see if it works, but oftentimes it does not happen that way. It happens the other way around, where you try some hunch, using some intuitive method, it works, and then backfit the math, because they should always, and while you are doing that exercise, while you are trying to explain your method using mathematics, because of the power of the math, you will also get a lot of corollaries and other generalization capabilities once you make it formalized. But most times you start with an empirical experimentation, at least that is what my experience has been. Okay, so we will write the math now. This is Ren, and you have Wxi squared. So let some x bar x cap is 1 by n. Is there a mistake? Oh, the summation should be outside, correct. Oh, where is the eraser? Yeah, call this as x cap. So then, and let sigma be this term. Using some notations, if I do this, then this thing would be, please verify this. This is simple algebra, right? I have vectorized the notations. If you, this is x cap, yeah. If you define the sigma matrix to be, okay, this is also sigma, this is also sigma, it's confusing. Let's do this and call this sigma cap to represent the matrix. This is the outer product of these two vectors, right? X minus x cap is a vector. You take the outer product of it, call that this is the variance or covariance matrix, right? So the objective function now can be written as W transpose sigma cap W. Okay, what do we want now? We want this to be maximized. So we want to seek a W star that would maximize W transpose sigma cap W. So this is a scalar, right? Sigma cap is a matrix. W transpose sigma cap W is the quadratic form, which is a scalar. So the objective function still is a scalar that we have, and this optimization is with respect to W. Now to your question, right? If you solve this optimization problem, what W it can choose? No, it can. You are solving a maximization problem. It can choose W to be having all the elements of W to be having very high value and solve this. So now you will have to constrain this. So how do you constrain this? We are interested in the direction W, not in the particular magnitude of that W. How do we do that? Normalize W's. So how do you normalize W? Add a constraint that this W vector that we are looking at, okay, has to have unit norm. Okay. Now you know the story, right? So how do we solve this? W star, write down the Lagrangian. The Lagrangian is W transpose times plus, take the derivative of this and put to 0, what will happen? So W star will be, do you know the solution to this optimization problem? This problem has a name, do you know this? No, this algorithm has a name, that's PCA, but this problem is called Rayleigh quotient, by the way. So what is the solution for this? W star will be the eigenvector of sigma cap corresponding to the largest eigenvalue. And this is your linear algebra 101, right? I think you should have solved this problem in your linear algebra. So this the solution for this Rayleigh quotient is, yeah. what's the question?
W3 is k cross 1. Sorry, vector k cross 1.
Correct. So
So how can you square the vector? Should be norm.
you mean here you are saying?
Yeah.
So Zi is a vector here, is it? Okay, let me see what this is. This is a k dimensional vector. Yeah, so what we missed is this norm square. Yeah, thanks for that. Yeah, makes sense. Okay. So now this W star will be the eigenvector of sigma square, sigma cap corresponding to the highest eigenvalue. Okay. Now, question? Okay. Now this W is called the principal component. So what's the dimension of W that we looked at now? It's a k cross D matrix, right? So now it has to have D vectors. No, it has to have k number of vectors, okay? And all of these are eigenvectors of the sigma cap matrix corresponding to the highest eigenvalues rank ordered, okay? So W's are called, let me just write that down. W which is a k cross D matrix will contain the eigenvectors of the covariance matrix, so rank ordered in accordance with their eigenvalues. See,
We are using W for the matrix also and the vector also.
see, you can make the k to be 1 and then the entire math goes through, and that will be the eigenvalue corresponding to the eigenvector corresponding highest eigenvalues. If you have 2 of them, then it will be the second eigenvector and so on.
So when we write L of W comma X, it is W transpose.
See, you can still write W to be a matrix. So what would this W, the solution for this the relay question problem would be a matrix W such that its columns are eigenvectors. Yeah, first k eigenvectors. That's it. Yeah. Now actually, right, you can take sigma matrix, which is the covariance matrix, is always positive semi-definite, right? Positive semi-definite. So it is guaranteed to have D eigenvalues always. So you can actually take D eigenvectors and get another space which does not have any compression, which does not give you any compression. But if you take the first k eigenvectors and project your data onto the space spanned by the first k eigenvectors, then you will have a representation that would have dimensions that is less than the data dimensions. Okay. Now, how do you choose? Okay, by the way, as some of you all already pointed out, this technique is called the principal component analysis. PCA. What is the hyperparameter here? K. How many number of eigenvectors do you want to take? You know, what is the dimension of what is the compression dimension that you would want to look at? In fact, depending upon how much of the variance of the data that you want to preserve, putting threshold on that, you can decide how much k do you want. Do you see why? Suppose you want 90% of the variance to be preserved, then you can find out, you know, how many eigenvectors that you would want to take to preserve 90% of variance and so on. If you take all eigenvectors, then you would lose nothing. If you choose first k eigenvectors out of d eigenvectors, then you would be losing some of the variances. Okay. And these individual eigenvectors are also called principal components, NENTS. Okay. The latest version has a spell check as well. Okay. Okay, this is PC. Okay, now I will give you an alternate interpretation of this, formulation of this, that which you should do as a homework, which is you should show that you will get the exact same formulation if you cast the problem as that of finding a linear projection of data such that the error between the actual data and the projected data is minimized. So, W times X will give you the projected data, Xi is your actual data. So, it is Xi minus W times X, take the norm of that, square of norm of that, sum it over all data points and minimize, find a W that would minimize that, will get you to the exact same solution. Can you see why? Because the algebra works out. Yeah?
How does the dimensional xi minus w?
It does not. So, you have to make your W to be having the complete dimensions, right, and then you only choose k of them, yeah, k vectors of them, that is it. You should show the equivalence between these two formulations, right, maximizing the projected variance or minimizing the projected error. So, that is why I made the mistake, right. So, when I talk of variance, I said it is minimizing, it is maximizing the projected variance or minimizing the projected error. Okay. Yeah, this is about PCA, and as you see PCA, why is PCA used? To reduce the dimensionality of data. Suppose you are given an image data set that has 10,000 pixels. Suppose you want to represent that using only 5 or 10 dimensions. The first go to algorithm is to do a PCA on your data and choose your k and represent that as vectors and then move on. Okay. Okay, this is about PCA. So, now PCA is limited by the fact that we are seeking a linear projection. Question?
That interpretation you said,
Yeah.
Xi minus Wx.
Yeah.
Will W become an identity matrix if you are taking W as D class?
Correct. So, that is a good question, right. The question is, if you make it to be a full rank matrix, then won't W be identity? So, how do you avoid that? You make it rank deficient. But adjust the dimensions, that is it. Okay. So, then it will not be identity, it can't be identity that way. Okay, this is about PCA. So, now let us, as I said, PCA is limited by the fact that you are only looking at linear projections. So, now why should you look at linear projections? The advantage of PCA is that you do not have to solve any optimization algorithm explicitly. I mean, you do have to, but you only have to solve an eigenvector problem, right, which is we have standard methods to that, the power method, etc. For large matrices it can scale up, that is the only advantage, but the limitation is that you are seeking a linear projection of data. Now, why should you only seek linear projection of data, right? So, how do you extend this idea to non-linear projections? So, how do we do this? So, to do that, what we do is that we define Z to be, okay, an MLP over X. It is not a linear projection anymore, it need not be MLP as well, it can be generally a neural network, so deep neural network over Z. Okay. Now, what is the task? We will have to formulate an optimization problem over here, right. What is the optimization problem here? Remember that our entire goal is to estimate the marginal distribution, because the moment you put semantics on top of it, that will become useless. So, we will have to ensure that the marginal okay, talking of marginal distribution, do you see why PCA estimates marginal distribution? Because the objective is set in such a way that the error between the data points in a statistical sense and the projected data is minimized, okay, which is it is trying to reconstruct the data back using the representations or Z, which is equivalent to estimating the marginal distribution. Okay, so now what should be the objective here? given that we want to estimate the marginal distribution. Now, recall that this representation now can be seen as p theta of z given x, right. Suppose you have a neural network, okay, that is taking x as an input and giving you z, can be seen as something that is estimating the marginal of z given x. If you want to estimate the the conditional of z given x. So, if you want to estimate the marginal p x from here, how do you do this? So, we know the math. How do we do this? Yeah, we can use the base rule and to estimate the marginal of this. So, what is p theta of x equal to in this case? Summation over this is what's it, let me write down this joint distribution now. So, this is equal to, hold on, let me just let's do that. So, now this is equal to p theta of x and z, yeah, this is what it is, right. So, we need to take a summation of this Is this all right? Okay. Now, how do we implement this in practice is the question. The way to do it is implementing above marginalization is to, let us say that you start with x and you have a neural network that will give you z. So, this is one neural network, let us call this E phi of x. Okay. Now, to marginalize, what you do is you take the z, okay, and pass it through another neural network d theta of z, get back another random variable x cap. Okay. Now, ensure that this random variable, distribution of this random variable, let us call that as p theta of x cap, matches with that of px. You can look at this entire thing as a compositional function where you start from x and then go to a latent space z, and from that latent space you have another neural network. So, what is this actually? So, x cap now is equal to, first start with x, there is one function E phi, and upon this function there is another function d theta that will give this random variable x cap. Now, make sure that this x cap, this distribution of this x cap is now matching that with the distribution of x. If it does that, then the z can be seen as a good representation of x. Why is that? So, you are able to recover the marginal distribution of x from the conditional p theta of z given x. Okay. Now, how do you ensure that, how do we match these distributions p theta of x cap and px? By again impose a distribution, take a KL divergence and minimize. If we assume it to be let us say a Gaussian distribution p theta of x and take the KL divergence, then you will end up getting a loss function. And what would that loss function be? So, whenever we are talking about Gaussian distribution and KL divergence between those two, the corresponding loss function would look like. So, this will be a function of theta and phi 1 through n. We have xi minus xi cap whole square, right. This is the loss function that you optimize it over, and this xi cap is now a function of theta and phi. So, therefore, optimizing this would give you an xi cap that would minimize, that would try to match the distribution of p theta of x. Do you know what is this called? This is called an autoencoder.
D time.
No, d theta is the decoder, this is the decoder, and this is the encoder. This entire architecture is called an autoencoder. Okay. So, typically what is done is you have a neural network and the encoder, which is E phi, will have this sort of an architecture, in the sense that you start from dimensions d and you come to dimension k, and we know that dimension k is always less because by construction, and from there you go back to the dimension of x, and this is the encoding, this is the decoding part. So, what do you do this? What do you do with this post training? You train it. So, this is autoencoders are always trained in an unsupervised way. Why? Because we are not using labels anyway. When this is standard backpropagation, you just train both of them using standard backpropagation. Now, once you train it, what do you do with it? Is the question. With all with all unsupervised methods, once you train this, take the data, pass it through the trained encoder, get the corresponding z's for every data point, and that becomes the feature or the representation for the data set. Instead of using x, use z. Make sense? And these are called embeddings. Z is called embedding. So, these E phi and d theta can be CNNs, they can be LSTMs, they can be transformers. Now, if you take a transformer and do this, so these are the BERT kind of embeddings that we look at, encoder decoder models. These are called the encoder decoder models, where encoder is a transformer, decoder is a transformer, and the task that you are trying to solve is the reconstruction. There is one twist to the tail here. In the modern day training, it is not the data reconstruction that is solved. Okay, what is done is you take the data point and perturb it with some noise, and then try to reconstruct the data back. Okay. So, now why is perturbation helpful in learning better representation? It is shown that if you perturb the input data points before autoencoding, they will lead to better representation. So, now why is that the case? Intuitively, if the decoder is, or rather encoder is trying to, the idea here is that the encoder will learn representations by ignoring the noise, and only if the encoder does it that way, then the decoder would be able to reconstruct data back. So, this is called denoising autoencoder. So, whatever I just wrote, where you take data point, perturb it with some noise and then do it, is called denoising autoencoder, and that is the workhorse of today's unsupervised learning LLMs. We will look into this in more detail in the next class, where I will talk about something called noise contrastive estimation, or NCE, which is an alternative estimation method to the maximum likelihood estimation. And this, which is denoising autoencoder, is a special case of NCE. I will show that it is a special case of NCE, and the current day LLM training, okay, is done by is done in two ways. One is that you take a sequence, randomly mask some of the tokens in that sequence, and ask your decoder to complete it, okay, which is very similar to the denoising autoencoder. The other way to do it is take a sequence. I mean, actually this is also a special form of whatever I said. Take a sequence, mask the last token, and ask your decoder to predict the last token. You can look into that also as masked autoencoding, but the mask is always applied at the last token, that is it, right. I will show that in fact the entire LLM space right now, okay, is trained using this way, where you have a reconstruction task that is there, and you just train it for predicting the next word. So, this is called unsupervised pre-training. There is a name for it, because there is no label that is being used here. You do what is called as unsupervised pre-training, and you do it on the entirety of the data that is available on internet, and it takes you a good 6 to 8 months on hundreds and thousands of GPUs to do this. But what is happening is backpropagation, on transformers with that scale with noise contrastive estimation. So, next class we will look at noise contrastive estimation as a way of estimating the underlying distributions, and I will give you a few examples for NCE, okay, using the mass prediction. And then we will go to another class of methods, which is another special case of NCE, which are called self supervised learning techniques, such as examples such as SimCLR and so on. And then we will move on to some introduction to generative models. So far in the course, none of our formulations can sample from the distribution, right. If we incorporate the sampling also in this, that becomes a generative model. We will see a few examples of that, and then we will conclude the course there. Okay. Thank you.